Next important topic is slip test for finding the values of direct axis reactance and quadrature axis reactance. Please see. So the direct axis reactance, how can you find out? From the slip test. Conduct the slip test here. V is the supply voltage, A is the ammeter, V is a terminal voltage, open circuit voltage. So from this diagram, apply 3-phase directly on load terminals. Apply the 3-phase directly on load terminals. Here they have 3 R, Y, B phases. Apply the 3-phase directly. Whenever you apply the 3-phase directly, the ammeter and voltmeter positions are changes from minimum to maximum continuously. That is, the meters are vibrating. So the meters vibrating means the meter needles are vibrating from minimum to maximum, maximum to minimum. The voltmeter also gives the minimum to maximum, maximum to minimum. Based on that values, we find out the xt and xq value. xt is equal to Vt by root 3 times of Ia. xq is equal to Vt Ia maximum by root 3 Ia. So from the test, we find out the direct axis reactance and quadrature axis reactance. Suppose we taken as sinusoidal waveform. This is a sinusoidal waveform. So where we have the quadrature axis, where we have a direct axis. Here please see. So this is a terminal voltage. Whenever the terminal voltage wave is minimum, definitely that is a value of xq. So please see, the terminal voltage value is minimum, that is the xq. Whenever the line current value is maximum, on that point the xq is there. Where the xq point is there, the voltage is minimum, current is maximum. Where the xt point is there, the voltage is maximum and current is minimum. So this is a simple method for finding the xt and xq values in alternator. Once again I repeat, in xq the voltage is minimum, current is maximum. In xt the voltage is maximum, the current is minimum. Please observe the waveform carefully, xq, xt and xq. This test conducted only in salient pole synchronous machine only, not for cylindrical pole machine. This is used for only in salient pole synchronous machines. So next one is the operating characteristics of synchronous machines. So the operating characteristics means whenever the alternator, definitely Eg is equal to Vt plus IaZs. Vt is equal to Eg minus IaZs. We know that from this expression or above expression, Eg square is equal to Vt square plus Ia square x square. From this equation, we draw the operating characteristics of machine. So operating characteristics means, so machine operated under lagging, leading and unity. So if you take terminal voltage here, the load current here, load current on x-axis, terminal voltage on y-axis, V phase is equal to E phase means, so wherever the V phase is there in terminal voltage, take the dotted lines. If you draw the graph, if you increasing the load current, in lagging load or inductive load, the voltage will be false. That is a lagging power factor. If you increasing the load current in unity power factor means resistive load, the voltage falls, but that is above with the lagging power factor. But in case of leading power factor, if you increasing the load current, that gives more voltage. Whenever the load current increases, the voltage also increases in leading power factor. So the exact characteristics here, please observe that one. If there is 100 voltage is a reference, so lag 0.9 lagging, 0.0 lagging, 0.9 leading, that is above the 100, 0.8 leading. All leadings are above the reference value, all laggings are below the reference values. This is the load characteristics of alternator. So the phasor diagram of two reaction theory already explained in previous session. So once again I repeat, assumptions are phasor armature resistance resistance approximately 0, generator is overexcited, EF is drawn horizontally. Here EF or induced EMF. Already I told that take VT or V phase is a reference diagram, references. So IA, ID are both are lagging. We draw the anti-clockwise. IQ and ID must be 90 degrees. That is a very important here. IQ and ID is 90 degrees. First we draw the VT. So another drop is IDXT, that is parallel with this one. So IQXP is 90 degrees from the IDXT. So this is a EF. From the Phasor diagram, flux psi is equal to phi plus delta. Phi is a angle between VT and IA. Delta is the angle between VT and IQ. Psi is equal to phi plus delta. So IQ is equal to IA cos psi, ID is equal to IA sin psi. Expression for excitation EMF in solid pole machine using Phasor diagram. From Phasor diagram, it is appears that EF can be found using EF is equal to VT plus JID XT plus JIQ XQ. But this expression cannot be used until we find the ID and IQ. And for it, we need to find out delta. ID is equal to IA sin phi plus delta, IQ is equal to IA cos phi plus delta. So first we need to find delta and then the magnitude of EF. For this we modify the Phasor diagram slightly. We find a voltage E dash using IA instead of ID or IQ, and this gives value of delta. Please observe the Phasor diagram once again. So triangle ABC is a phi, BC is equal to IQ XQ. We have to find the length of AB in terms of IA. Cos psi is equal to BC by AB. That is the IQ XQ by AB. And we know IQ is equal to IA cos phi. From that find out AB is equal to IQ XQ by sin. And second expression IQ by cos psi is equal to IA from the Phasor diagram. Putting 2 in 1, AB is equal to IA XQ. AC is equal to ID XQ. From that one, EF is equal to VT plus JIA XQ. VT is known, IA is known, XQ is known. So we can easily find out EF dash, which will give the information regarding to delta. After finding EF dash, we can find EF using even arithmetic equation. EF dash and EF are in phase. EF dash is equal EF dash plus ID of XT minus XQ. Or we can use delta to find the magnitude. EF is equal VT cos delta plus ID XT. So power output in solid pole machine. Output is equal, already we know VIA cos phi. Now phi is equal phi psi minus delta. P output is equal V into IA cos psi minus delta. VIA cos psi into cos delta plus sin psi into sin delta. Output power is equal VIA cos psi cos delta, VIA sin psi sin delta. We know IA cos psi is equal to IQ, IA sin psi is equal to ID. Power output is equal V cos delta IQ plus V sin delta into ID. We can see active power output is sum of all the product of in phase component of current and voltage, multiplying numerator and denominator by XQ in first term and XT in second term. We get output power is equal V cos delta XQ into IQ XQ plus V sin delta XT into ID XT. IQ XQ is equal to V sin delta and ID XQ is equal to VEF minus V cos delta. Power output is equal V cos delta by XQ into V sin delta plus V sin delta by XT EF minus V cos delta. So that is nothing but V square by XQ sin delta cos delta plus VEF XT sin delta minus V square XD sin delta cos delta. So overall power output is equal to V into EF XT sin delta plus V square by 2 1 by XQ minus 1 by XT sin 2 delta. First one is a per phase power output from solid pole. This is excitation power. This is a reluctance power. So this is a characteristics of solid pole machine. So normally in non-solid pole machine, the angle between power versus delta is a pure sinusoidal from 0 to 180, that gives a half of wave. But here the solid pole machine, that is a different. So total power is a This the characteristics will be like here, the excitation power here, the reluctance power is here. So normally the operating angle delta is lies in between 45 to 90 degrees. Different techniques for synchronization. So this is a very important method. So what are the methods used for synchronization? For synchronization we have three methods: three dark lamps method, two bright, one dark method. Third one is synchronous scope method. So in this method of synchronization, two bright, one dark method means, so if you follow that one, if the L1 is connected in phase 1 line, L2 is in same line, L3 in line B. Three lines are connected in three switches that is connected to alternator. For synchronization is a very important in alternator, because the number of alternators are operated in parallel in generating station. So we see the methods. Lamp L1 will go dark and lamp L2 and 3 will dimly glow but equally glow, as they are connected between different phases, and due to this there will be in phase difference of 120 degrees. In order to we have connected in two alternators are in phase, definitely lamp L1 will must go the dark and lamp L2 and 3 will dimly glow. Synchronization of alternator using synchronous scope. This is a instrument. Whenever the synchronization is matches, the needles comes in 12 o'clock, exact 12 o'clock. If the that is not synchronization, the needle of will be rotating clockwise or anti-clockwise. The pointer rotates in anti-clockwise if the machine is running slow, or it is rotate clockwise the machine is running fast. The correct instant of closing synchronizing switch is when the pointer is right upwards. Okay, thank you.